Hi, my name is Darshan Patel, and this is my lab for Physics Lab 3, Black Hole and Orbits. So in this lab, this is some background. So a star is orbiting a black hole of an unknown mass located at the origin. The star has a mass of 2.0 times 10 to the 30th kilograms. The position data should be in x and y coordinates, and the star will be generated in the starter code, so the resulting star trajectory was unique to me based on my student ID. And so some instructions for this lab were we analyzed the star's motion to find the net force on the star for all points in the dataset using the scaffolding starter code beginning on line 112. We also assumed that the net force on the star was due solely to a black hole located at the origin, and that the time between data points in our trajectory was 1 Earth day, which was in seconds. Using the results of my analysis, I estimated the mass of the black hole. So this is some of the code that pops up. So we had to make the values, so we had to figure out what dp/dt was, code for that, the fnet and everything. And for the 1 day, we had to just multiply like how many hours there are in a day by how many minutes are in a second and how many hours are in a minute. So it looked like 24 times 60 times 60. And this is our end product, as you see in the glow script on the right side, where you see the star and the black hole and the forces acting on it through the arrows. And for Excel, after getting all the data from the glow script, we copy and pasted all the values into Excel, and then we used an Excel function to find the average of all the values to find the average mass of the black hole. And this is like some of the data, and so we just, on the left side is the raw data, and then on the right side is the average of all the raw data. And then the background. So for part 2, the background is that I am in a spaceship approaching the system, and that I just simulated. As I got closer, I noticed that there's a planet orbiting the star, and the planet has a moon. I land my spaceship on the moon and take a look around, and then decide to take a look around the planet. Then I take my spaceship into a fancy orbit and make sure that it does not crash into the moon. And then I use my glow script to simulate the motion of my spaceship around the planet and the moon by calculating all the necessary gravitational forces and using Newton's second law to predict the motion of the moon and my spaceship. So writing the code, the starter code already has the masses of the planet, moon, and the spaceship, and the planet is at the origin and motionless. The moon is to the right of the planet and initially moves in the positive y direction. The spaceship is sitting on a hill that is 100 meters tall above the surface of the moon, on the side of the moon that faces towards the planet. I will need to determine what initial velocity the spaceship needs to have, such that I can get it to move in an orbit around both the planet and the moon without crashing into either one of them. The spaceship cannot travel faster than the speed of light, and it may even be possible to get a stable, fancy-looking orbit because of the complications of the code. So I just had to make sure that the spaceship didn't crash into either the moon or the planet. And so in the calculation loop, I calculated all the forces on the moon, like F-grav on the moon due to the planet and F-grav on the moon due to the spaceship, and all the forces on the spaceship, like F-grav on the spaceship due to the moon and F-grav on the spaceship due to the planet. Once I calculated the net forces acting on each the moon and the spaceship, I will need to use Newton's second law and the position update formula to make the moon and spaceship move. So this is some of the code that I made, and this is the trajectory of my spaceship, and you can see that it doesn't crash into the moon even after a long time iteration. Some of the things that I had to change though was the ship speed X and the ship speed Y, so that would help avoid me crashing into the moon. And for the discussion, these are some of the answers to the discussion questions, and the net force on an object is the measurable cause of motion, while the rate of change of momentum describes how an object's momentum changes over time. According to Newton's second law of motion, they are equal and their parallel components change the object's speed, while perpendicular components change the direction of the motion. For the second question, to model the motion of a black hole, star, planet, and moon, the computational model must include all gravitational interactions between every pair of objects using Newton's law of universal gravitation. While every interaction contributes the most massive objects like the black hole would likely dominate the system's motion.